Wait, you said toads are usually tan?
Yeah.
They're not green?
But this one wants to toad though, because it has more warts.
Do frogs have warts? Wait, let me see it again.
Yes.
I would definitely think the green one looks more toadish. It's bigger.
It's bigger. That's the thing.
It could be a bullfrog. Bullfrogs are way bigger.
That is true.
You see,
Could
bullfrogs have that circle thing behind their eyes.
you know what a frog's ear is called? It's called membrane. You called that?
I know that like amphibians can't see, you know, but
Well, we have one, so you can fight over it. All right.
A lot of those today.
All right. It's not a copious amount. All right, let's go ahead and get started. Today. All right. Okay, today we are going to cover the trapezoidal rule. Okay, and this is quite similar to rectangular or Riemann sums. So if you know how to do that, today should be quick, and then you can get on to working on stuff. So take your little graph here, split it based on the ordered pairs that you're given. And then do you remember for a Riemann sum, you would pick a side and make a rectangle by cutting straight across. So like, for example, don't do this, but just watch. A left Riemann sum, I'd be like, you're the height, you're the height, you're the height, you're the height. You remember that? That's not what we're doing today, so don't draw that. Oh. What we're going to do today is we're going to use rectangles with slanty tops, okay? So what I mean by that is that you're going to take these two and instead of picking a side, you're just going to connect them as is. Okay, and what is a four-sided shape where one of the sides is slanty? It's a trapezoid. Very good. So what we're going to do is we're going to construct trapezoids, calculate their total area, and that'll be our approximation for the area. Okay, so this will be trapezoid number 1. Okay, let's do the next one. You'll connect straight across the top. That'll be trapezoid number 2. Okay, the next one, you'll connect straight across the top with a straight line. That'll be trapezoid number 3. And then the very last one we'll say is trap number 4. Straight across the top. All right. Okay, so how do you calculate the area of a trapezoid? Okay, 1/2 base 1 plus base 2 times height. And then remember that whichever sides are parallel, those are the bases. So what you should notice is that for your trapezoids, okay, the 2 parallel sides are the y values. So when you do area in trapezoidal, your bases will be the y and the y on the left and the right. So here's what I mean by that. Come down here to the bottom. We know there's a 1/2. And then you're going to add the first and second y value because they're base 1 and base 2 of the first trapezoid. So this height is 5. This height is 8. And then the height is gonna be the delta X between them. So really, this is Y1 plus Y2. And then multiplied with delta X, if you want to kind of write like this version of that. Okay, now if I'm going from 0 to 2, what's my delta X? 2 plus. Okay, now we're on to trapezoid number 2. Put your 1/2 in the front. I'm going to add both of the Y values, but I want you to notice that for trapezoid number 2, what is its first base? What number? 8. So 8 was already a base 2 for the first trapezoid, but now I'm reusing it as the first base for the yellow trapezoid. So it'll be 8 plus 10. And then the width between them should be measured along the x-axis. So from 2 all the way to 5, how wide is the base? The delta x is 3. Very good. Plus. Now we're on trapezoid number 3. I'm going to do 1/2. I'm going to add the two y's together. So this one's a 10, this one's a 17. And then the width between them would be from, this is a 5 all the way to 10. How wide is that? My delta x is 5. Okay, one more left. Last trapezoid, what are the y values? We're going to reuse 17 and 20. And then remember that the delta x is the distance between the x's, not the distance between the y's. So if this is 10 and I'm going to 14, what's my delta x? Okay. And then you would put that in the calculator, blah, blah, blah. You get the idea? All right, go ahead and turn the page, please. All right, so we are going to do another trapezoidal rule. You have the graph already there for you. So let's go ahead and do it. And our goal is going to be to move away from using the graph, because a lot of times on the AP test, they're just going to give you the table. So put your 1/2. We're going to add the first two y values. What are they? 20 and 32. And then we're going to multiply by the width between their x's. So from 0 to 30, what's the width? 30. Delta x is 30. Okay, plus. Then we're going to add the next two y's, but we're reusing 32. This time, 32 will be partnered with 41. And then the distance between their x's is how far from 30 to 40? 10. Okay, next one. 1/2 always in the front because it's part of the trapezoid formula for area. Now I'm doing 41 plus 55. And then the distance between their x's from 40 to 50 is 10. Okay, next one. I'm doing 55 and 65. And then what is their width between their corresponding x values? 20. Very good. One more trapezoid left. 65 and 72. And then the distance between their x's would be. All right, now, if you were actually in the homework, you'd have to add it up, but for the notes, we're not going to. Okay, now let's talk about the difference between this and this. So we kind of ignored this when we were doing Riemann sums, but you should know what this is finding. So look at your thing. Okay, this is R of t, and it says that R of t is the rate of fuel consumption in gallons per minute. Okay, recorded during a plane flight. Okay, where R of time is t minutes. Okay, blah, blah, blah. So this is gallons per minute. That's what you're looking at. If you do an integral or area on gallons per minute, what would your units go back to? You remember doing this? Gallons. Very good. And then you would put it back into the context of the story. So what are these gallons of? Fuel consumed by what? The plane over 0 to 90 what? Time is measured in minutes. So the integral from 0 to 90 represents the total gallons of fuel used, or you could put consumed if you wanted to be fancy, okay, by the plane during the flight from 0 to 90 minutes. Okay, but for the AP test, you would have to include that the fuel is measured in gallons and that the time is measured in minutes, and then you're just kind of reapplying it back to the story. Okay, let's pretend that you added this up and it came out to 1,000. Okay, just pretend. So over the 90 minutes, they used 1,000 gallons of fuel. If I divide that by 90 in the front, that would be the average fuel consumption back in gallons per minute. Okay, think about if that makes sense. That I'd take how much fuel they use, divide it by how long they were in flight. That would be their average gallons per minute. Okay, this is the formula that you learned last week. Do you remember 1 over b minus a, integral a to b? Okay, that is the average y value. And so usually on the AP test, they're gonna either ask you to say what this represents or this. Here's the difference. When you do an integral, gallons per minute goes back to gallons. But if I do gallons per minute back to gallons, and then I divide by 1 over b minus a, which in this case would be 1 over 90 minus 0, okay, then it turns it back to gallons per minute. Because you're dividing how much fuel they used by the 90 minutes they were in flight. So this would be the average fuel consumption rate in gallons per minute over 0 to 90 minutes in flight. Okay, so I know it's like kind of confusing that they look so similar. Okay, but if they put the 1 over b minus a in front of it, okay, then that's going to turn it back into a rate like it was at the beginning. Okay, so let's try the next one. Okay, this time we have oil leaking out of a tank. Okay, and then it says, what's it measured in? What's the rate measured in? Gallons per hour. So if I just do the integral, what are my units going to be now? Gallons. So this would be the number of gallons leaked from the barrel. Oh wait, tank, whatever. Okay, over 0 to 18. And then what are my time units? Hours. Okay, the number of gallons leaked from the tank over 0 to 18 hours. But now I'm going to take the total gallons leaked and divide it by, sorry, it's not 18, but it should be, just pretend. Okay, now let's say I put a 1 over 18 in front of that. Okay, this should be 18, so it matters. Okay, then I'm going to take the total gallons leaked, divide it by 18 hours, then that would be the overall average rate of how fast the oil was leaking. Okay, so this would be the average rate that oil was leaking in gallons per minute, or was it out? Gallons per hour over 0 to 18. So if you just do the integral, your gallons per hour goes back to gallons. But as soon as you divide it by 18 hours in the front, now it's right back to gallons per hour. Okay, then let's set up your trapezoidal sum. So remember, it's 1/2. Add the first two y values together. What are we adding? Add the y values though, 40 and 38. And then you're gonna multiply by their width, which is what? 3. Okay, next one. Now we're adding 1/2. What two y values? 38 and 36. And then their distance between their x's is how many? 3. Now, peek ahead at the rest of the chart. Do you notice it's always 3? Okay, because it counts by 3 every time. So it goes 0, 3, 6, 9, 12, 15, 18. So we're going to keep going, but you can kind of just expect that it's always 3 for this one. So for my next one, it'd be 30 and 26. And then I'm going to put plus ... Okay, the reason that I'm going to put plus ... is because if you remember, for Riemann sums, if your delta x is always the same, do you remember that you could just like pull it out? So if it was like the width was always 5, you could just do 5 in the front. Do you remember that? Okay. You can do the same thing here, but you can pull out more than just the 3. What else do they all have in common? They all have a half. So if you want to do the short version, because your delta x is always the same, pull out the 1/2 and the 3. And then you're only going to add the y values, but this is really important. This is different from Riemann sums. When you add the y's, 40 is only in there once, but then 38 is in there how many times? Twice, because remember I had to reuse it. Okay, same thing with 36. It's going to get used twice. Same thing with 30. It's going to get used twice. The only ones that won't get double counted will be the first one in the table and the last one. Everybody else will be doubled. So what I'm going to do is I'm going to put 40 plus, and then I'm going to double my 38, and I'm going to double my 36, and I'm going to double my 30, double my 26, double my 18, but then only single count my 8. Okay, so this would be the equivalent of the short version, but you can only use the short version if your width is the same for all the 7. So make sure you single on first and last, double all the interior ones. Good on that? All right, turn the page. All right, let's go down to number 3. Okay, so it says use the trapezoidal rule. Is my width always the same? 0, 3, 6, 9, 12, 15, 18. Is it always the same? Then we can do the short version. So 1/2, my width is always 3. And then remember that when I add up my y's, I'm going to single count first and last. I'm going to double count all the middle ones. So it'd be 22 plus double 17, double 13, double 10, double 7, double 5, single 2. Now, the long form for trapezoidal sum will still work. But to me, this is just a lot easier if you have the same width every time. All right, now let's do our represents. Okay, let's read the question. It says, coal gas is produced at a gas works. Pollutants are removed by scrubbers, which become less and less efficient as time goes on. R of T represents the rate scrubbers are removing pollutants during production measured in tons per month. So if this is tons per month for my R of T graph, what will the regular R of T's antiderivative be? Back to tons. So this integral represents the number of tons. Okay, and then we would just have to go back and kind of put it in the story. Tons of, okay, it says pollutants that are being removed. So number of tons of pollutants removed by the scrubbers. And then you would just put over whatever timeline it is. So in this case, it's 0 to 18. And then if this was tons per month, then I can see my time would be measured in months. So if I integrate tons per month, it goes back to a number of tons. What about if I divide the total number of tons by 18 months? Then it's back to tons per month. So this would be the average rate of pollutant removal in tons per month over 0 to 18 months. But remember, it's because this is the formula for the average Y value. And so because it's an average Y value, your units should not change because you do an antiderivative, but then you divide back by the units that you just got rid of. Okay. Does that kind of make sense? Get it? Okay. We're gonna skip to this page right here and talk about over or under. Okay, and then I accidentally put the unit circle in your notes. I don't know how this happened, but disregard. Okay. Yeah. Just 7 is fine. All right, take your first graph, 0 to 9. I want you to break it up into 3 subintervals and draw in a trapezoidal sum. So if I'm going 0 to 9, do you remember how to find the width? You do b minus a over n. So if I'm going from 0 to 9, that'd be 9 minus 0, and then we're dividing into 3 subintervals. So 9 minus 0 divided by 3, what's my width each time? 3. So go into your graph, and I want you to cut it into 3 equal pieces. So we'll go 0 to 3 to 6 to 9. Okay, it doesn't have to look perfect, just do your best. So we're cutting it into 3 equal pieces with a delta x of 3 each time. And then I want you to draw in your trapezoids. So I would connect here to here, here to here for trapezoid number 2, and then here to here for trapezoid number 3. Now remember, these trapezoids are estimating the exact area under the curve. So I'm going to shade that in for you here. Okay, this is my exact area under the curve. How do my trapezoids compare? Are they too big or too small? They're too big. Very good. So we're going to put here that your trapezoidal sum will overestimate the true area when. Now, for Riemann sums, you care about if the graph is uphill or downhill, but look at this graph. When it was downhill, was the trapezoid too big? When it was uphill, was the trapezoid still too big? Okay, on each side, the trapezoids are too big. So it doesn't actually matter whether it's an up or downhill graph. What matters is the concavity. So if your graph is concave up, your trapezoid will be too big. Concave up. The trapezoidal sum will overestimate the true area when the graph is concave up. Okay, we're now going to do the same thing with the bottom graph. Okay, so go ahead and splice your area into 3 pieces. But actually, let's just cut it in. Let's just go here to here to here. So we're only going -3 to 3, but I'm just going to divide it into 2 pieces. Okay, and then I'm going to connect the endpoints to make my trapezoids. And then I noticed that my trapezoids in this case are what? They're too small because the real area under the curve is going to actually exceed how much area my trapezoids catch. So in this case, my trapezoidal sum will underestimate the true area. But the reason that happens is not because it's an increasing or decreasing graph, it's because of the concavity. What is the concavity on that bottom graph? When graph is concave down. So concavity determines how your trapezoids end up. All right, we have one more question left, and it's a make your own table. So let's go ahead and take a look at number 5. In your calculator, will you find the width? Remember, it's B minus A over N. So if I'm going from 1 to 8, what will the top of my equation be? 8 minus 1. And then it says, estimate the value of the integral using a trapezoidal sum with 4 equal parts. So 8 minus 1 is going to be 7. 7 divided by 4 is, I don't know, 1.75. Thank you. Okay, so my width is going to be 1.75. Every single time. I need to make a table that goes with that. So right here, draw me a little table. We're going to start at what number? 1, and we know we're going to stop at 8. Okay, but in the table, I need it to count by 1.75. So let's review how to do that in your calculator so it does all the work for you. Okay, first thing you're going to do is go into y equals and type in the equation that you want, which is x squared minus 1. Okay, x squared minus 1. Okay, then you're going to hit second window, and you're going to let your start value be the value you want it to start at, which is what number? 1, and the delta or the triangle is what you want it to skip by. So I want my table to start at 1, and I want it to count by 1.75. Okay, then once I've done that, I can hit second graph and look at my chart. Okay, so at 1, my value is 0. At 2.75, my y value is 6.5625. 4.5 is 19.25. Then 8 comes next. Wait, did I miss one? 6.25 thing. And at 6.25, it's 38. Now, remember what we talked about last time? Because on your homework, you need your answer to be correct to the 3rd decimal, you really should go to 4 in your table. So like at 19.25, you see how that is just 2 decimals. That's fine. But on the one below that, it's going to round it. I don't want it rounded here. So I'm going to put 38.0625. And then at unit 63. I do not, but if you need to go back. Yeah. Okay, then from there, do I do long or short? I can do the short because my width is always the same. So let's just put it straight into the calculator. So it'd be 1/2. What's my width every time? 1.75. And then I'm going to open a parentheses. Remember, in trapezoidal sums, nobody gets skipped. Some people get doubled, but nobody gets skipped. So it'd be 0 plus 2 times 6.5625, 2 times 19.25, 2 times 38.0625, and then just 163. Okay, so if you got 166, that would be the correct answer. Y'all got it? Now, if this was your Delta math, it's gonna say you want it rounded to the nearest thousand. So if my answer is 166.90625, how would I round that for my thing? Very good, 906. Okay, so for the ones where you're making your own table, remember you want your table to go to 4 decimals so that at the end, when you round, you don't have a rounding error. Yes. Uh-huh.
The decimal at 38.06.
Great question. So if your decimal is cut off, you're talking about the 38 you said?
Yeah.
If you just scooch over to it, you can see the full decimal below it.
Oh.
Yeah. So now sometimes look at the one above it for the 19.25. That one really just is 2 decimals. So in that case, you wouldn't have to like add 2 zeros to make it 4 decimals. But if it is longer than 3, you want to be exact until you're rounding. Okay, then look at your graph. Is it concave up or concave down? Up, then how would my trapezoids be? Too big or too small? Too big. So look at your picture for a concave up graph. Your trapezoid is an overestimate. Okay. So we would put here, this is an overestimate because graph is concave up. And then how did we know that? We just looked at the picture, right? They give you an equation. You just look at how it's bent. If it's up like a cup, then it's over, down like a frown, it's under. All right, that being said, take out your computers, log into Delta Math. We're going to do the first graphing one together, and then y'all have some time to work. Yeah. Okay. Yeah. Take the time.
Sorry to go back.
No, because you have the area. You can plug it into the calculator if you have an equation. If you don't have an equation, remember, for absolute value, you just add the area.
Yeah.
And then if no absolute value, you count the above says positive, below says negative.
I think that's the point. Like, it makes me dirty. I lost my good water. And I only have one water bottle instead of 2.
All right, go into the very first one and determine your width for me, please. Why not? Oh,
Thursday.
okay.
Oh, that meant Friday. But yeah, we're getting blocked a lot right now.
That's okay. Just try not, once you know, you get kind of behind. It can be kind of hard to get back.
Yeah.
You know? Okay, first question. What's your width? From 2 to 10, how wide is that? 8, and I want to divide it into how many pieces? 4. 8 divided by 4 is 2. Then push go. It'll divide your graph into pieces for you. Oops, mine didn't. Okay, but then once it does it, I'm going to have to log out and log back in to fix it. Remember, both corners need to be on the graph. Okay, so once you hit go, hopefully it breaks yours up. And then both corners need to be on the thing for it to work. Let me just open it. Did it work? Come on, baby. Okay, good. So both sides of this need to make it onto the graph. So I'm going to pull my middle up and then make it crooked. Middle up, make it crooked. Now, it might be kind of hard on these to tell whether it's too big or too small, but remember, it's not that hard to tell if it's concave up or concave down. So for this graph, is it concave up or down? Down, then look at your notes. Is it going to be an over or an under? Under. Also, if you look, can you tell, even though the pocket of area missed is pretty small, you can tell that it's too small. Okay, and then we'll put because the graph is concave down. Okay, remember, increasing and decreasing makes no difference for trapezoidal sums. What matters is the contact. And then y'all should be able to finish it, hopefully from there.